In this lecture, we will discuss about binary mixing model. In this, what I will be presenting is, if you have two sources and they mix in particular proportion, how that mixing equation will look like and what will the chemical or isotopic composition of the mixer depending on the fractions and the source composition. These find frequent applications in the source tracing, even you want to quantify like the mental and crustal contamination, how that is influencing the total composition of a particular magma. These kind of processes require some of this mixing model. So, I have splitted this course into two parts. First, I will discuss the theoretical equations and for single element, for two elements and for isotopes and for two isotope systematics, how they look like, that I will present theoretically. Then I will use certain examples, use an Excel to create mixing trends for various of these combination of chemical elements and their isotopes. So, we will start with the theoretical part first. Once we are done, we will go to the computer and see how that can be used for real time problems. So, we often try to look for chemical and isotopic composition in different reservoirs, and when they mix, we always see a mixer and their chemistry is available. You want to go back and quantify how much is coming from where. So, let us say if you are looking for an estuarine system, this is not limited to a estuary or a river, there can be various possible sources, multiple sources, but I will give an example for two sources and you can use that for several sources basically. So, if you have a estuary is a mixer of river and sea water. Now, this mixer was created because a element X that is there in river, element X in sea water mixed in particular fractions to form the estuary, right. It is a mixer and you want to quantify how much is coming from which source, so that you can make mass balance calculations. To give an example, let us say strontium in a mixture will be equal to strontium that is coming from source A, F into the fraction of water supplied by the source A, strontium B into Fb. Now, because this is a closed system, the Fa and you have only two sources, the Fa Fb should be equal to 1. So, you can rewrite this strontium A Fa plus strontium B into 1 minus Fa. So, here if you are talking of estuary, then you are talking of fraction of water coming. If you are talking of sediment mixer, then you are talking of sedimentary fractions, but sometime you may require to use this as strontium by sodium, the ratios may be needed. In that case, please remember, if you creating a equation of strontium by sodium into A, and let us say this is a Pa and strontium by sodium in B and 1 minus Pa. Here this P is not about fraction of water or sediment, you are basically representing here the fraction of this element that is mixing here. So, here the P reflects fraction of sodium coming from source A. Okay. Instead of taking single element like strontium, if you have two elements, how the binary mixing will look like. Let us say strontium, which is in a mixer, will be strontium A into F plus strontium B into 1 minus F. So, we are talking of two sources F, A and B. They mixed in a particular proportion F and 1 minus F to produce a mixture, and the strontium mixture will be of this form. Now, if you have another element like calcium, this will be calcium A into F, calcium B into 1 minus F. The F will not change because you are talking of the same two sources and they are mixing. So, this F is not going to change. So, if you solve this for F value, F will be equal to, so now this equation becomes calcium M will be calcium A into F plus calcium B minus calcium B into F. So, this is actually F means calcium M minus calcium B, calcium A minus calcium B. So, this is let us say equation 2. Now, use this F expression in 1, strontium M will be strontium A calcium M minus calcium B divided by calcium A minus calcium B plus strontium B and 1 minus F. So, I will write this 1 minus F, which will be calcium minus calcium B, calcium A minus calcium B minus calcium M plus calcium B. So, these two cancels out. So, basically strontium M is equal to strontium A calcium M divided by calcium A minus calcium B minus strontium A calcium B divided by calcium A minus calcium B plus strontium B calcium A by calcium A minus calcium B plus or minus this term strontium B minus calcium M, strontium B calcium M divided by calcium A minus calcium B. If you rearrange this, strontium M will be equal to calcium M, taking calcium M common from these two, strontium A minus strontium B divided by calcium A by calcium B plus these two terms, which is strontium B calcium A minus strontium A calcium B divided by calcium minus calcium B. I have just rearranged that. So, what comes out is that strontium M, let us say if this is Y, this calcium M, let us say it is X, this is a constant term, is in slope form, and again this is a constant term because calcium A, calcium B, strontium A, strontium B are not going to change. So, basically you have a linear equation. So, now if you plot that, let us say you have calcium of the mixture, strontium of the mixture here, and let us say this, let us say this is calcium and strontium. Let us say your source A is here, your source B has a composition, because you know the source A and source B compositions. If you mix A and B in different proportion, they will follow a straight line depending on how much supply is coming. If you have 0% of B, the mixture will have this number, this will be 20% of B, this is 40% of B, this is 60% of B, this is 80% of B. So, basically depending on the fraction of mixing of A and B, these two elements will form a linear trend, and that is how the binary mixing will look like. I will now discuss how two sources with different isotopic compositions creates a mixture, and how the isotopic ratio of that mixture varies, that we will discuss. We will discuss that for 87 strontium by 86 strontium, but if you want to extend that to any isotope systematic, that should hold good. So, if you try to create this equation for 87 strontium, let us say in a mixture. So, basically what we are trying is, we have a source A, we have a source B. Let us say this is 87 strontium in A, this is 87 strontium in B. They have mixed in particular proportion. Let us say this is F, then this has to be 1 minus F. Then you are creating a strontium, then you are creating an isotopic mixture, 87 strontium mixture, and we are looking for an expression for this mixture and its 87 strontium composition. So, this 87 strontium mixture will be equal to 87 strontium in A into F plus 87 strontium in B 1 minus F. Now, what is 87 strontium A means? This is strontium A. If you divide that with its atomic weight, okay, you will get moles. If you multiply that with Avogadro's number, you will know the number of atoms in that, and then if you multiply that with abundance of 87 strontium in A, then you will get the 87 strontium A term, then you have a F, and then same for B, you have a strontium B, atomic weight for strontium in B multiply by Avogadro's number, which is not going to be different, and then you will have abundance of 87 in B multiply by 1 minus F. Okay. So, this is our 87 strontium in the mixture. Let us say I want to write the same equation for 86 strontium for mixture, that will be exactly similar. Strontium A multiplied by atomic weight of strontium in A multiplied by Avogadro's number. Instead of 87 abundance here, this will be abundance of 86 in A into F plus strontium B, atomic weight of strontium in B, Avogadro's number, abundance of again 87 becomes 86 here. So, that is in B into 1 minus F. So, this is the expression for 87 strontium mixture. Now, we are interested for 87 strontium by 86 strontium. If you divide these two, 87 strontium by 86 strontium, and you can assume that atomic weight for strontium A, atomic weight for strontium B nearly equal, because in natural systems the isotopic abundances does not change drastically like that happens for samples or spike. So, in this case you can safely assume that the atomic weight for strontium A and strontium B are same. If you do that, then this expression simplifies to strontium A Na atomic weight of 87 A into F plus strontium B into Avogadro's number, abundance of 87 B into 1 minus F divided by strontium A Na abundance of 86 A into F, strontium B into Na abundance of 86 B into 1 minus F. I just rearrange them, the atomic weight A, B has been cancelled out. So, you will have this expression. We will rearrange this further. So, these Avogadro's numbers cancels out. Now, this equation becomes 87 strontium by 86 strontium in the mixture will be equal to strontium A 87 abundance of 87 in A into F plus strontium B abundance of 87 in B into 1 minus F divided by strontium A abundance of 86 A into F plus strontium B abundance of 86 B into 1 minus F. We know 86 is a stable isotope. So, abundance of A and abundance of 86 B will be pretty much equal. So, if you divide this, so if you consider abundance of 86 in A is equal to abundance of 86 in B, then this equation 87 strontium by 86 strontium for M will be equal to, I will just divide by abundance of 86 in all the terms. So, you will have strontium A into 87 strontium by 86 strontium in A F plus strontium B 87 strontium by 86 strontium B into 1 minus F divided by strontium A F plus strontium B 1 minus F. If you see carefully, so this abundance of 87 divided by abundance of 86 is actually the isotopic ratio. That is why I could write 87 by 86 in strontium. If you see this term critically, we know this is the strontium in the mixture. So, this 87 strontium by 86 strontium in the mixture is equal to strontium A 87 strontium by 86 strontium A divided by strontium M plus strontium B 87 strontium by 86 strontium B into 1 minus F. So, this is actually, if you see 87 strontium divided by strontium M, it is in a hyperbolic form, right. X into y is a constant term which comes out to be a hyperbola term. So, if you try to present this, so if you have a strontium M, I am sorry, if you plot strontium versus 87 by 86 strontium, and you know that this is the source A composition, this is the strontium concentration and this is the strontium isotope ratio for A, and you know the composition for B, this is the strontium concentration and this is the strontium isotope ratio for B. Then if you mix these two using different fractions, they will follow an hyperbolic trend and these will be their fractions. Depending on the fractions, the mixture composition will fall in any of the points in the hyperbola trend. So, we can write this if I assume that R is actually 87 strontium by 86 strontium. So, this can be R strontium will be R1 strontium 1 F1 plus R2 strontium 2 1 minus F1. So, what we discuss is 87 strontium by 86 strontium in a mixture will be, so there was a strontium M term, 87 strontium by 86 strontium A into strontium A into F plus 87 strontium by 86 strontium in B is a concentration in B 1 minus F. Okay. If I assume that R is actually 87 strontium by 86 strontium, I can write this Rm is strontium m is equal to R1 strontium 1 F plus R2 strontium 2 1 minus F. I can write similar equations for all the isotopes I am interested in. Let us say I am interested in for something like neodymium, 143 neodymium by 144 neodymium. I am representing that as E. So, this equation will be Em into neodymium m will be equal to E1 strontium E1 neodymium 1 F plus E2 neodymium 2 1 minus F. Now, if you find an expression for F here and put in that equation and solve it, you will see that mixing of two different isotopes like 87 strontium by 86 strontium and 143 neodymium by 144 neodymium, if I plot these two and if I know the composition for source A and source B, then they will also follow a hyperbolic trend. I want you to derive this. So, you can find an expression for F in this equation, put the same equation in here, you will see that these two isotope ratio and their mixing is expected to follow a hyperbolic trend. Now, we will go to the computer and try some of the real time problems that how these mixing trends can be generated in a computer. Now, I will show some of the examples how this can be used or how the mixing trends can be generated. Let us say I am taking two elements strontium and calcium, two elements with the source 1 and source B. Let us say strontium A is about 100 ppm and let us say calcium is 10%. So, basically strontium being a trace metal, it should be in ppms, whereas calcium which is a major element, let us say that is in weight percent, and let us say strontium B is highly enriched in strontium, let us say it is 100 and calcium let us say that is 30%. We will try to prepare a mixture with different fractions. As the fractions for coming from source A are 0, 0.1. So, we are creating different fractions. So, it can vary from 0 to 1 maximum. So, we will try to find out what is the fraction mixing composition. If it is 0, this will be. So, you remember the equation we discussed, strontium m is equal to strontium A into F A plus strontium B into 1 minus F. This is what the equation that we discussed. So, we will try to use this. So, to find here, so this should be strontium A which is 100 multiply by strontium F A which is 0 in this case plus strontium B which is 1000 multiply 1 minus F. So, that is 0. So, the D4 is a constant. So, that will not change with the mixer. I will just put a so basically because you have 0 coming from source A, so this is 100. If you do the same calculation for different fractions, so basically at 100% of source A this became 100 ppm, for source B if it is 0 then it becomes 1000 and there will be a internal variation between these two. Now, let us say if you are going for calcium, if you do the same thing, you follow the same equation. So, this is 30, it is varying between 30 and 10. Let us plot this. Insert so our source 1 x will be calcium, y will be strontium. So, this is our source A. We can add another source, which is let us say source B. I made a mistake here. So, this I am correcting. So, this is strontium A. Alright. So, these are the two sources. This is source A, this is source B, and let us plot the mixing trend. Select data, add. So, we are plotting the mixing actually, mixture values varying from fractions. If you take x value, so these are the x values, and if you take the y value, so these are the y values. So, they will follow a straight line. That is what we understood from the that is what we understood. So, this is the this is a source, your this is calcium in weight percent, and this is strontium in ppm level. So, the sources, if you see this, if I plot this chart type, so here is your source A, source B, and this is the mixing line, and we read in the lectures that this should follow a straight line. Now, instead of these two isotope, let us say we used a isotopic ratio, let us say strontium ratio by 87 by 86 strontium. You remember that we discussed that R m strontium m should be equal to R 1 strontium 1 F plus R 2 strontium 2 into 1 minus F. This is the equation that needs to be followed. Let us say for strontium, which is a lower concentration, is expected to have a higher 87 by 86. So, let us say we will make it 720, and let us say source B is 705. We will try to find out what is the mixer value. So, the mixer value has to be R m will be equal to R 1 strontium 1 F plus R 2 strontium 2 1 minus F divided by strontium m. So, we will use this. So, what is there? R 1. So, this is R 1 multiplied by strontium 1, this is the strontium 1 F. So, this is the F plus R 2, this is R 2 into strontium 2, this is strontium 2, 1 minus F, 1 minus F and divided by strontium mixer, which is the E8. We have already calculated the mixer for this one. So, this is the final expression. These are the source composition for different fractions, they are not going to change, that is why I am putting these terms. So, because you have a source A 0, so that should be equal to 705. So, if you, so this should vary between 705 to 705. So, now if we plot the same thing, let us say select data, we are doing that for mixture. So, in the x axis we will be taking the strontium composition concentration, and in the y place we will take the isotopy ratio. They should follow a hyperbolic trend. So, that is what you are able to see here. So, these are the hyperbolic trend. So, this is the source B, this is this, because 720 this is source A. So, you have a source A and source B, they follow a mixing, and that is a hyperbolic trend. So, this is for two elements that we discussed, this is for different strontium isotopy ratio that we discussed. Let us say we will do the same thing for two isotopes. We have a 87 by 86 and strontium. Let us say we take this for epsilon neodymium. So, neodymium, which is actually 143 by 144 neodymium. The variations are pretty small, that is why they often represented as a epsilon neodymium. We will discuss about the epsilon unit later, but if you are given with neodymium concentration also, let us say if this is 5 and let us say this is 20 and let us say this is 5 and let us say this is minus. So, let us say this is epsilon neodymium value is 5 here and let us say this is 15 here, because these are concentration terms. So, you will follow this equation, and because these are epsilon units, they are isotopy ratio. So, this will be used. So, first this multiplied by 0 plus this multiplied by 1 minus 0 . So, these will be the equations, and this will be the mixing numbers for neodymium. If you do the same thing for neodymium, I am sorry, there is a mistake here. So, I need to fix the source composition, because with fractions they are not going to change. I will just fix it so that calculation becomes correct. So, now it is correct. Now, for strontium, if I write the same equation for neodymium, so it will be I am just following the strontium equations for make it easier. So, if I do the same, I got this equation which varies from 5 to 15. Now, if I plot the two isotopes, let us say strontium isotope and neodymium isotope, select data, add, we are doing this for a mixture, and in x axis we are trying to put the mixture value for strontium, and the y axis we are trying to put the epsilon neodymium value. So, they are following again a hyperbolic trend. This is your source source B, this is your source A, and the mixing of these two will create an strontium isotopic ratio. So, if I put the terms here, so this is basically 87 strontium by 86 strontium, and this is epsilon neodymium. So, this is how. So, if you have two elements, the mixing should look a straight line. If you have strontium isotope changes, so if this is like strontium in ppm and this is 87 strontium by 86 strontium. So, that follows a hyperbolic trend, and if you have two isotopes like strontium isotope and neodymium isotope, that will also follow a hyperbolic trend. So, this is how you have to do calculations for mixing. So, if I know this data, let us say this number is given to me, I should be able to calculate what fraction is coming from what sources. Thank you.